What if I told you that swapping our Milky Way with just one specific galaxy would transform every night on Earth into a brilliant stellar showcase? That's the reality of living in Andromeda, our nearest galactic neighbor. This massive spiral galaxy contains over 1 trillion stars compared to our Milky Way's modest 400 billion, creating a night sky packed with starlight beyond anything we've ever experienced. But here's the flip side that comes with all that cosmic beauty. More stars mean more stellar deaths, and more stellar deaths mean more supernovas exploding throughout the galaxy. Each of these cosmic explosions sends waves of high-energy radiation racing through space, and Earth would sit right in the middle of this stellar violence. The sheer scale of Andromeda means we're not just talking about a prettier night sky. Living in Andromeda's stellar neighborhood. We're talking about moving into a galaxy that spans 220,000 light-years from edge to edge, which makes our Milky Way look like a compact car parked next to a freight train. While we're sitting pretty with about 400 billion stars in our galaxy, Andromeda houses over 1 trillion stars crammed into that massive space. That's more than double the stellar population density, and every single one of those extra stars would fundamentally change what Earth experiences on a daily basis. Step outside on any clear night in Andromeda, and you'd witness something that would make our current night sky look pathetic by comparison. The stellar density would be roughly twice what we see now, pushing the visible magnitude limit far beyond our current 6th magnitude threshold. Instead of the few thousand stars visible to the naked eye from Earth's surface, you'd see tens of thousands scattered across the sky like someone spilled diamonds on black velvet. The familiar patterns we've used for navigation and storytelling for thousands of years would vanish completely, replaced by entirely new stellar arrangements that follow Andromeda's different spiral arm structure. But here's where things get interesting in a terrifying way. All those extra stars aren't just pretty lights hanging in space for our viewing pleasure. They're cosmic time bombs, each one destined to die in spectacular fashion. Studies show Andromeda's supernova rate could be 1.5 times higher than ours, which means more stellar deaths and more high-energy radiation events. The increased stellar population creates a galaxy where cosmic violence happens at a much higher frequency than what we're used to in our relatively quiet Milky Way neighborhood. Right now, we're still in the safe zone of this galactic swap scenario, but the real problems are just getting started. The fundamental mechanics of how our solar system moves through space would change dramatically once we factor in Andromeda's different structure and gravitational environment. Our galactic year, the time it takes our solar system to complete one orbit around the galactic center, would stretch from 225 million years to roughly 500 million years. This massive change happens because Andromeda's larger diameter means our solar system would sit much farther from the galactic center, requiring more time to complete each orbital cycle. Earth's geological timescales would need complete recalibration, with major evolutionary periods and extinction events spaced across entirely different cosmic rhythms. Andromeda's spiral arms would subject our solar system to gravitational influences we've never experienced before. The galaxy's massive dark matter halo, which weighs approximately 1.5 trillion solar masses compared to our Milky Way's 1 trillion solar mass halo, would create stronger gravitational gradients throughout the galactic disk. Our solar system would experience different tidal forces as it moves through Andromeda's spiral arms, potentially affecting the stability of planetary orbits over very long timescales. The interstellar medium surrounding our solar system would become significantly more turbulent due to stellar winds from Andromeda's enormous population of red giant stars. These aging stellar behemoths constantly shed their outer layers into space, creating streams of hot gas and charged particles that flow between star systems. Our solar system would encounter these stellar wind streams more frequently, creating additional pressure on our heliosphere, and potentially compressing the protective bubble that shields us from galactic cosmic rays. Any future space missions attempting to navigate beyond our solar system would face complete chaos. The star patterns that form the backbone of celestial navigation would be totally scrambled, with familiar reference points like Polaris and the Southern Cross replaced by entirely different stellar configurations. Spacecraft would need to rely heavily on internal navigation systems and radio beacons, since using stars for directional reference would require completely rewriting every navigation protocol ever developed. Andromeda's denser stellar environment raises the odds of supernova hits and comet dislodgements by a factor of 2. The increased stellar density would create more frequent gravitational interactions between passing stars and the outer regions of our solar system. These close encounters, while still extremely rare on human timescales, would occur roughly 2.5 times more often than in our current galactic environment. Each passing star would exert gravitational tugs on objects in the Oort cloud, the spherical shell of icy bodies that extends nearly 1 light-year from our Sun. The Oort cloud contains trillions of potential comets, most of which remain frozen in stable orbits at the very edge of our solar system's gravitational influence. However, when passing stars disturb this delicate balance, they can nudge these icy bodies toward the inner solar system, setting them on collision courses with the planets. In Andromeda's more crowded stellar environment, these gravitational disturbances would happen more frequently, destabilizing approximately 30% more Oort cloud objects over geological timescales. This means Earth would face a steady increase in comet impacts, with the bombardment rate rising significantly above what we experience in our current galactic neighborhood. While individual comet impacts might seem insignificant compared to asteroid threats, the cumulative effect over millions of years could trigger more frequent mass extinction events. The beautiful stellar dome visible from Earth's surface would come with this hidden cost. Every spectacular night sky view would remind you that your planet sits in a galaxy where cosmic violence occurs more frequently, and comet impacts pose a persistently higher threat to long-term survival. But even Andromeda's dangers would pale in comparison to what awaits in galaxies where the night sky doesn't just glow with starlight, but burns with something far more deadly. The Quasar nightmare scenario. Now imagine living in WISE J22460, 526 plus 032 70652, one of the brightest quasars ever discovered, where the galactic core outshines 100 billion suns and bathes any planet within thousands of light years in lethal X-rays. This isn't your typical spiral galaxy filled with peaceful star formation and organized stellar neighborhoods. This is a quasar galaxy, powered by cosmic violence on a scale that transforms the entire galactic environment into something resembling the inside of a nuclear reactor. At the heart of this galactic nightmare sits a supermassive black hole weighing billions of times more than our Sun. That's roughly 1,000 times more massive than the black hole, sitting quietly at the center of our Milky Way. But mass alone doesn't tell the full story of why this galaxy would spell instant doom for Earth. This black hole isn't dormant like ours. It's actively feeding, devouring matter at a rate that creates the most violent and energetic phenomenon known in the universe. The galaxy's active galactic nucleus creates an environment where the central region alone outshines all the stars in the galaxy combined. Think about that for a moment. Every single star in this massive galaxy, from red dwarfs to blue supergiants, produces less total light than the glowing inferno surrounding the central black hole. The accretion disk, where matter spirals inward toward its doom, glows brighter than entire stellar populations. From Earth's surface, you wouldn't see individual stars at night because the galactic core would dominate the sky like a second sun that never sets. The real terror comes from what this feeding frenzy creates. As matter accelerates toward the black hole, it gets compressed and heated to temperatures exceeding several billion degrees. At these temperatures, atoms get ripped apart, and charged particles move at significant fractions of light speed. Active galactic nuclei accelerate particles to near-light speeds, creating cosmic death beams that extend thousands of light-years into space. These particle streams turn the galaxy into a massive accelerator where high-energy radiation floods every corner of space. Gamma rays, X-rays, and ultraviolet radiation stream outward from the galactic center at intensities that would make a nuclear bomb look like a birthday candle. Earth wouldn't just sit in a galaxy with these conditions. Earth would exist inside a cosmic microwave that operates at lethal power settings 24 hours a day, every day, for millions of years. The accretion disk around the central black hole operates like a cosmic blast furnace, heating and fouling matter to billions of degrees and creating X-ray and gamma radiation storms that propagate throughout the entire galaxy. These aren't brief bursts like the gamma ray events we occasionally detect from distant galaxies. These are constant, steady streams of deadly radiation that would bombard Earth's atmosphere continuously. Earth's atmosphere would begin disintegrating within centuries, rather than lasting the billions of years we have left under our current sun. The intense X-ray and gamma radiation would break apart nitrogen and oxygen molecules in the upper atmosphere, creating a cascade of chemical reactions that would strip away our protective atmospheric layers. The ozone layer would vanish completely within decades, leaving Earth's surface exposed to the full fury of the quasar's radiation output. But atmospheric destruction represents just the beginning of Earth's problems in this galactic environment. The gravitational chaos created by matter constantly falling into the central black hole would send shock waves rippling through the galaxy's gravitational field. These gravitational disturbances would affect stellar orbits throughout the galaxy, creating a cosmic environment where planetary systems face constant destabilization. The stellar population throughout the galaxy would also change dramatically due to the extreme radiation environment. Massive stars would have their lives shortened even further as intense radiation pressure strips away their outer layers. Stellar winds would become more violent and extensive, creating a turbulent interstellar medium filled with high-energy particles and electromagnetic radiation. Even at our current distance from the galactic center, roughly 26,000 light-years away, Earth would be positioned well within the quasar's lethal radiation zone. The inverse square law means radiation intensity decreases with distance, but the quasar's energy output is so extreme that even at interstellar distances, the radiation levels would be catastrophically high. Space missions would become impossible, as spacecraft electronics would be fried by radiation within hours of leaving Earth's magnetosphere. Satellites in orbit would fail rapidly as high-energy particles destroy their sensitive components. Radio communications would be disrupted by the constant electromagnetic noise from the galactic center, making long-distance communication nearly impossible. Ocean temperatures on Earth would rise dramatically as the planet absorbs increasing amounts of high-energy radiation. The water cycle would become chaotic as intense radiation heats the upper atmosphere, creating massive storms and weather patterns unlike anything in Earth's geological history. Ice caps would melt rapidly, not from greenhouse gases, but from direct radiation heating. Living in this quasar galaxy means Earth's surface would receive thousands of times more deadly radiation than our current cosmic background environment. Every square inch of the planet would be bombarded with gamma rays, X-rays, and high-energy particles at levels that would sterilize the surface within months. The beautiful night sky filled with brilliant quasar light would be the last thing any Earth observer would ever see. But even this cosmic furnace of radiation and gravitational chaos would seem peaceful compared to finding yourself caught between two massive galaxies in the middle of a high-speed collision, where the very structure of space itself becomes a battlefield. Collision course in the Antennae galaxies. Picture this. You're sitting on Earth in the middle of two massive galaxies smashing into each other at 300 kilometers per second. The Antennae galaxies aren't just casually bumping into each other like two people in a hallway. They're engaged in a full-scale cosmic demolition derby, where 800 billion stars from both galaxies get flung around by gravitational forces, so intense they make our solar system look like a toy boat in a hurricane. This collision creates an environment where the basic rules of galactic structure go completely out the window. Instead of neat spiral arms and organized stellar neighborhoods, you get pure chaos. Stars that spent billions of years in stable orbits suddenly find themselves launched across intergalactic space at speeds that would make your head spin. The gravitational tug-of-war between the two galactic cores turns the entire system into a cosmic pinball machine, where stars are the balls and gravity provides all the bumpers. From Earth's surface, the night sky would display something that would make even the Andromeda scenario look tame. Massive tidal streams of stars stretch across 500,000 light-years of space, creating brilliant ribbons of light visible to the naked eye. These aren't subtle features you need a telescope to spot. These are cosmic highways of stars bright enough to cast shadows on Earth's surface. The streams curve and twist through space like enormous cosmic rivers, each one containing millions of stars that got ripped away from their home galaxies by the collision's gravitational violence. But here's where things get really dangerous for Earth. The gravitational encounters happening throughout this galactic war zone are so intense that they're launching entire stars completely out of the galaxy at incredible speeds. We're talking about stellar velocities that reach thousands of kilometers per second. These hypervelocity stars become cosmic bullets flying through space with enough kinetic energy to devastate any planetary system unfortunate enough to be in their path. Some of these ejected stars carry their own planetary systems with them, creating rogue solar systems that wander through intergalactic space. The collision triggers what astronomers call a starburst phenomenon, where star formation explodes to roughly 30 solar masses per year. That's about 10 times the normal rate you'd see in a quiet galaxy like our Milky Way. This means the collision is forcing gas clouds throughout both galaxies to collapse and ignite into new stars at an unprecedented rate. The result is a cosmic baby boom where massive, hot, short-lived stars get born in clusters throughout the collision zone. Here's the problem with all that rapid star formation. It creates approximately 10 times more supernovas than you'd normally expect in a stable galactic environment. Each of these exploding stars releases more energy in a few seconds than our Sun will produce over its entire 10 billion year lifetime. The collision zone becomes a cosmic fireworks display, where massive stars burn through their nuclear fuel in just a few million years before exploding in spectacular death throes. The supernova rate increase means Earth faces constant bombardment from high-energy radiation, gamma rays, and cosmic particles streaming out from stellar explosions happening throughout both galaxies. While individual supernovas might occur hundreds or thousands of light-years away, the sheer number of explosions creates a background radiation environment that would gradually strip away Earth's protective atmosphere over geological timescales. The collision disrupts the interstellar medium in ways that create additional hazards for our solar system. Shock waves from the galactic collision propagate through space at hundreds of kilometers per second, compressing gas clouds and triggering violent chemical reactions in the space between stars. These shock waves carry enormous amounts of energy and can travel across entire galactic regions, affecting star formation and stellar evolution patterns throughout the collision zone. When these shock waves reach regions near our solar system, they could compress local gas clouds to the point where they collapse and begin forming new stars. This process might sound harmless, but it could potentially create massive hot stars uncomfortably close to Earth. These new stellar neighbors would be blue supergiants with surface temperatures exceeding 20,000 degrees and luminosities thousands of times brighter than our Sun. The shock waves from the galactic collision could also destabilize our solar system's Oort cloud, that spherical shell of icy objects extending nearly a light-year from our Sun. Compression waves traveling through the interstellar medium would squeeze and stretch the gravitational field holding these frozen bodies in their distant orbits. This destabilization would send swarms of comets streaming toward the inner solar system, dramatically increasing Earth's chances of experiencing major impact events. The gravitational chaos extends beyond just flinging individual stars around. The collision gradually pulls the two galactic cores closer together in a death spiral that will eventually result in a merger. As the cores approach each other, they create increasingly violent gravitational disturbances that ripple outward through both galaxies. These gravitational waves would be strong enough to detect from Earth using sensitive instruments, providing a constant reminder of the cosmic violence happening at the galactic center. The merger process itself would create the most spectacular astronomical event visible from Earth. The two supermassive black holes at the centers of each galaxy would orbit each other with increasing speed and decreasing separation. When the black holes finally merge, they would release more energy in gravitational waves than all the stars in both galaxies produce in electromagnetic radiation. While the night sky would provide an incredible light show with brilliant star streams, constant aurora displays from high-energy particles, and the slow-motion spectacle of galactic merger, Earth would face a 200% increase in supernova-related extinction events compared to our current galactic environment. But all this cosmic violence and brilliant stellar chaos would seem overwhelming compared to a galaxy where the opposite problem creates an entirely different kind of nightmare. Lost in the darkness of Dragonfly 44. Dragonfly 44 presents the complete opposite scenario, where stepping outside at night would feel like being trapped inside a sensory deprivation chamber. This galaxy weighs roughly the same as our Milky Way, but here's the cosmic joke. You wouldn't be able to see any of it. The entire night sky would be almost completely black despite sitting inside a galaxy that contains the same gravitational mass as our star-packed home. The mystery of Dragonfly 44 reveals one of the universe's most bizarre configurations. This galaxy contains roughly the same amount of total matter as our Milky Way, which should mean hundreds of billions of stars lighting up the cosmic neighborhood. Instead, 99.99% of the galaxy's mass exists as dark matter, that invisible substance we can't see or directly detect, but know exists because of its gravitational effects. The remaining 0.01% of visible matter gets spread across only about 100 million stars, compared to our Milky Way's 400 billion stellar population. Those 100 million stars sound impressive, until you realize they're almost entirely aging red dwarf stars with surface temperatures barely hot enough to sustain nuclear fusion. Red dwarfs produce such feeble light output that even our closest red dwarf neighbor, Proxima Centauri, remains invisible to the naked eye despite being only 4.2 light-years away. Now imagine an entire galaxy populated almost exclusively with these dim stellar embers scattered across hundreds of thousands of light-years of space. Space navigation in this galactic environment would become completely impossible using traditional methods. Human civilization has relied on stellar navigation for thousands of years, from ancient Polynesian voyagers crossing the Pacific to modern spacecraft using star trackers for orientation. The Vikings reached new worlds by following star patterns across the North Atlantic. Without bright reference stars scattered across the night sky, these civilizations would never have developed the astronomical knowledge needed for long-distance exploration. The absence of visible stars would fundamentally alter human cultural development in ways that extend far beyond navigation. Astronomy wouldn't exist as a science because there would be virtually nothing to observe. Ancient civilizations built their calendars, mythologies, and religious systems around stellar patterns and celestial movements. The zodiac, constellation stories, and seasonal star cycles that form the foundation of human astronomical understanding would never have emerged in a galaxy where the night sky remains perpetually dark.